So this video is going to be the introduction that we have to 3D figures. Normally in geometry, what we've been working with so far is 2D figures, triangles, rectangles, trapezoids, all drawn on kind of a piece of paper, which is two-dimensional. And the reason that we know they're two-dimensional, not only because we know what 2D means, is because the way dimensions are described in geometry, those shapes have two of them. So if I draw let's say a rectangle, it has two dimensions. It has a length and it has a width, or some people say base and height, same thing. But those are the dimensions of that rectangle, this way and this way, length and height, or if you want to be, again, more traditional, you'd say length and width, is how it's usually said. Same thing for say, a triangle. Even though it has three sides, it generally goes this way and it goes this way. That's how a triangle is drawn. It's drawn left to right and top to bottom. Or think about it this way: if I was like a computer, you know how sometimes in movies they have those computers or robots that are drawing things really quick by going up and down and just kind of sketching. Um, that would be a two-dimensional shape because you can sketch this by breaking it apart into small little segments that go up and down and just kind of arranging them left to right, almost like a puzzle. And again, you might be thinking about, okay, well, can't I go diagonally as well? Well, yes, we can go diagonally like that, but that's really just a combination of left and right. Like this one right here means I'm moving this much over and this much up. So it's still a left-right direction, so we still call it a two-dimensional shape there. The diagonal really isn't its own dimension. It's a combination of the two dimensions of the left and the right, or the base and the height, essentially. So that's why these shapes are 2D shapes. Whoops. That's why these shapes are 2D shapes, because they can be drawn, like I said, in this two-dimensional way of drawing their left and right movement and drawing their up and down movement, and you can get the shape. Three-dimensional shapes are named that way because you need three dimensions in order to describe them. You still have the left and right and up and down movement like 2D shapes do, but you also have this front and back. Some people call this the depth. Some very pretentious people call it the breadth. This is not usually used, but it's kind of a fancy way of saying it if you want to look smart. Um, but everything has a left and right, everything has an up and down, but only 3D shapes and above have a front to back measurement. So, for instance, this cube here would be a three-dimensional shape. Now, it's drawn on a 2D space, obviously, but it's considered a three-dimensional shape because you're supposed to picture this as this being the front. So I'll put like a little label here. Let me do this in a different color here. This face right here, the one in green, that's the front. So that right there is the front. And this blue one right here, let me do it this way. This blue one in back, that would be, as I just said, the back. So if I can try to draw some contrast here, so that would be the back. So again, it has to be kind of shown like this in a 2D space just to get some perspective, but this is how you would think about it, as the front and the back. Usually the dotted lines like you see here that I just kind of drew over. So if I backtrack there for a minute. There we go. These dotted lines here are meant to be stuff that you're not supposed to. This is like behind the shape. So whenever you see a dotted line in a 3D shape, think about, okay, that's the back corner, and the stuff that's not dotted is kind of up front. Okay. So one more. There we go. So we have a few things that we talk about when it comes to these shapes here. We talk about vertexes, edges, and faces. So a vertex is simply a corner. So think about vertex as the corner of a three-dimensional shape. It's where basically you have a meet of three or more edges. So this is where uh, three or more, try it again. A vertex is a corner, or put another way, where three or more edges meet. So if you have three or more edges meeting at one single point, then that's where you get the vertex. An edge, obviously, is sort of like the quote-unquote side of a 3D shape. It's those lines like here. That's an edge, that's an edge, that's an edge, that's an edge. These dotted lines in back are all edges. They're just edges in the back of the shape that you're not quote-unquote supposed to see. Um, those can be described as a meeting of two faces. So when two faces meet, they form an edge where they intersect. So this is the intersection of two faces. This is the intersection of three or more edges. So three or more edges intersect to make a vertex. Two or more faces intersect to make an edge. And then a face is simply the flats of the shape. So that's like this green and this blue, those would be faces. This top and this bottom would be faces. The left and the right would be faces. So those are kind of the flat sides of an object. I shouldn't say sides because we're talking about edge being a side, but they're the flat sections of the three-dimensional shape. And so a cube here has a front, back, left, right, top, bottom. So a cube has 6 total faces. 2 for front and back, 2 for left and right, and 2 for top and bottom. And then it has a total of, well, let's see here, we have 1, 2, 3, 4 edges on top, 1, 2, 3, 4 edges on bottom, and 1, 2, 3, 4 edges going up and down. So that's a 4, 4, 4, so that'd be a total of 12 edges. And then in terms of vertex, well, it has 1, 2, 3, 4 corners, 1, 2, 3, 4 corners on the bottom, so it has 8 vertexes. So 8 vertexes, 12 edges, and 6 faces. And again, it kind of makes sense because well, I won't go there. That's getting a little bit too into detail with what I was just about to say there. So we'll just keep it at that. So 6 faces, 12 edges, 8 vertexes, or vertices as it's properly called. So how do we define these 3D shapes? Because again, with polygons, we had definitions. So remember, a polygon was simply a shape that had all straight sides. It was closed, which means that all the sides kind of connected back to each other, and then the sides did not intersect with other sides except at the endpoints. So, for example, we had these polygons that we're very familiar with, and we had these that are not polygons. So this shape right here isn't closed because it's open right here. This shape intersects at points that are not the endpoints, like right here. That's not an endpoint. That's the middle of a side. And right here again, excuse me, that's not an endpoint. That's the middle of a side. So this is not a polygon either because it's kind of intersecting itself here. Whereas these are nice, good polygons. You could also have concave polygons, which were when they kind of collapsed in on themselves. That'd be a concave polygon there. And we had name for these, right? Like this right here would be a triangle. This would be a rectangle. This would be a 1, 2, 3, 4, 5. This would be a pentagon because it was a 5-sided object. So we have the general term of polygon, and then we had specific terms depending on how many sides it had. So for 3 dimensions, we kind of do the same thing. We just basically take the 2 dimensions and build it up. So the 3-dimensional equivalent for a polygon is called a polyhedron. Let me try that again. Is a polyhedron, or hedron, depending on how you want to say it. Some people say polyhedron, some people say polyhedron. It's just a matter of what your taste. So again, polygon is 2D object. Polyhedron is 3D object. And that kind of goes back to the Greek wording of it, polygon, gon being kind of side, I believe, for Greek, or something to that effect there, and then hedron being more face rather than side. So polyhedron means multiple faced. So again, polyhedrons have different faces, whereas polygon, gon means sides, where 2D objects more have their sides than faces. So a rule for a polygon for a 3D object, sorry about that, extra noise. The basic rule for a polygon for a 3D situation is defined as this: a solid with all flat sides that enclose a single region of space. So this would be kind of the definition of a polyhedron in words. It has a solid, so it means that, again, it's a closed shape essentially, with all flat surfaces that enclose a single region of space. So again, this is a polyhedron here. It has all flat surfaces, so flat all the way around. It encloses a single region of space, and this part here encloses a single region of space, and solid kind of mean the same thing in that it's not open. So think about, like, if I had, I'm not going to be able to draw it, but let's say I had kind of like an open box, like here, and then here, and then here. So kind of think like a box that's been cut open. This would not be a polyhedron because even though it might be a 3D shape, it doesn't enclose a certain space. It's open to the outside. So that's kind of the same issue that, whoops, back up. That's kind of the same issue that this had here, that it was an open space rather than a closed space. So polyhedrons need to do the same thing. They need to kind of close in on each other where they're not left open to the open air, essentially. So these are all examples of polyhedrons. These are not polyhedrons, even though they are 3D objects. So everything here is a 3D object, but again, their main concern is that they're all curved. So cylinder has curved edge, cone has a curved edge, sphere has a curved everything, and then torus, which is kind of like a mix between a sphere and a cone, or kind of like a donut, as most of us refer to, has curved um, all the way around. So again, any curves means it's not a polyhedron. There are 3D objects, but there's no special name for it. It's just non-polyhedrons. Whereas if it's all straight edges, then it's a polyhedron. So think about a polyhedron is basically the 3D version of a polygon, is the layman's way of describing it. So we can also classify polyhedrons further, just like polygons. We can classify them further based on their characteristics. So we first started to talk about the basic one of prisms. So prisms are polyhedrons that have two parallel and congruent bases. So bases that are basically polygons that are connected by parallelogram faces. So now parallelogram faces could also mean rectangle and square. So remember, rectangles and squares also count as a parallelogram. So that's the formal definition. So what's kind of that translated into normal speak? So basically, a prism is what you get when you connect when you connect the corners rather of two congruent. Let me just do this. This should be easier. When you connect the corners of two congruent and parallel polygons. So parallel meaning that they're kind of lying in space where they wouldn't intersect each other. So for example, rectangular prism, you have a rectangle down here. You have another rectangle up here. And you have them being connected at their corners. So connect the corners, connect the corners, connect the corners, connect the corners. So that's a rectangular prism. Two parallel polygons that are congruent. So these rectangles have the same base and height. They're the exact copies of each other. They're parallel because they would never intersect. So as long as this one stays up here and this one stays down here, the way they're arranged, they would never intersect. And then therefore it makes a prism. Triangular prism, same way. You have a triangle on top, parallel. Let me do this one actually. Parallel to the triangle on bottom, and then you connect their corners and you get your triangular prism. Notice how the reason this is a triangular prism, not another rectangular prism, by the way, is that if I said this was a rectangular prism, then I would mean that the bases are obviously rectangles. So I could say maybe, well, what about this base and this base? Why can't these be my bases? Well, if these are my bases, it breaks the first rule, which is the bases have to be congruent, which they might be, but they also have to be parallel. And clearly these two faces here, these two rectangles are not parallel because they intersect right here. There's an intersection of their edges at this spot right here. So these cannot be my bases because they're not parallel. They might be congruent, but they're definitely not parallel. So that's why it's a triangular prism, because the bases that are congruent here and parallel, again, the key word there being and parallel, are the top and bottom, which is why it's, again, a triangular prism. And again, this goes for any type of polygon. So a pentagonal prism, again, you have a pentagon on top, you have a pentagon on bottom, and then again you have the parallelogram or rectangular faces along the edges. Again, a rectangle is a special type of parallelogram. So if these are all squares, rectangles, or parallelograms, those all count as parallelogram faces. Um, so basically, the way we classify prisms is what type of base they have, essentially. So you can make any polygon into a prism. You can have an octagonal prism, a decagonal prism, a dodecagonal prism, a 20gonal prism. It's just a matter of what base do you have. So if you want a 20gonal prism, that means you have a polygon with 20 sides on bottom. You have the copy of it, exact same congruent polygon with 20 sides on top, and you just connect their corners. So you can create any type of polyhedron you want using that method there. And they don't necessarily have to be straight up and down either. So for example, a triangular prism could look like this. You have a triangle here. I'll make sure I get an exact copy of this. Woo. Guys, one more time. Lock that in place. So you have a triangle there. Let's say you copy it. And you have a triangle over here, and then you connect these bases as best we can here. Let me do a little bit thinner line. So there, there, there. This would still be a triangular prism, because even though it's kind of slanted or off to the side, it's still polygon, polygon. They're parallel, they're congruent, and they're connected at their corners. So it's still a triangular prism, even though it's kind of tilted a little bit. So that's a fine prism as well. So what about a pyramid then? Let me lock this in place too while I'm at, just in case I need to do something similar. So a pyramid is another type of polyhedron, um, and a sorry, a pyramid is a polyhedron that has one base, not two, but one base, and three or more triangular bases that meet at a common point, or as we typically call it, vertex. So one base, three or more triangular faces that meet at a common vertex. So the translation of that, again, to layman's terms, because it's a very technical math term, is a pyramid is what you get when you take a polygon, once again a polygon, and you connect all the corners of it to a single point, usually above or below the polygon. Or again, they can be slanted as well. So just like prisms, they're usually classified based on the shape of their base. So whatever the base is shaped as, that's what we call the prism as. So a triangular pyramid, or sorry, whatever the shape of the base is, that's what we call the pyramid as. So a triangular pyramid, you have a triangle on bottom, and then all three corners are not connected to another triangle, but all three meet at another point above the triangle. Again, a rectangular pyramid, you have a rectangle on bottom, that's your base, and then all the corners of the rectangle are connected to a single point. Pentagonal pyramids, same way. And again, you can have an octagonal, decagonal, 20gonal pyramid, all doing the same idea. Get your polygon on bottom, take all the corners, and meet them up at a single point. Or again, it could be below two. So if I have a triangle, and I draw the corners here, so I can draw it down there, and then down there. And that's a triangular pyramid as well. So it doesn't necessarily have to be above the shape. It can be below the shape too. And then what about regular ones here? So we had regular polygons, right? So for example, a pentagon that was regular. Let me see if I can't get one here. So here we have a regular pentagon. And what we meant by a regular pentagon was that all sides are equal. So if this side was 5, all the sides were 5. And all angles were equal. So if one angle was, let's say if one angle was 60, all the angles were 60. So that was a regular polygon. All sides congruent to each other, all angles congruent to each other. If a polyhedron is regular, it's a little bit different. All the faces are regular congruent polygons. So all the faces take the same shape with the same size and the same angles. And all the edges are congruent. So basically what you can think of here is all the distances between the faces are congruent. So if you travel from face A to face B, it's the same distance as traveling from face C to face D, essentially. So the best way to describe this in layman's terms is basically if all the sides of a polyhedron are congruent, then it's a regular polyhedron. So by sides here, we're talking about edges. I should probably use the correct lingo here. So edges. So if all edges of a polyhedron are congruent, then it's a regular polyhedron in most cases. Now that's a very loose definition there because there are some strange cases where you can make it so that it's not necessarily like that. But to kind of make the language into more of a layman's terms, that would be the best I could do there. Um, Now, unlike polygons, where you can make as many regular polygons as you want, you can make a 20-sided regular polygon. But for polyhedron, there actually are only 5 different ways this can happen. There are only 5 regular polyhedrons in the entire world. And these are actually a very crucial study in a lot of geometries called the Platonic solids. It's a very, very, very well studied and even still studied aspect of geometry because they were kind of not necessarily discovered, but they were really heavily investigated and studied upon by an ancient Greek mathematician called Plato. And so once again, no matter how hard you try, there are only 5 types, there are only 5 regular polyhedrons you can actually make. There's the tetrahedron, which is basically a triangular pyramid where, again, all the edges are equal. Bottoms, tops, everything is equal there. And again, all the angles are equal in these faces here. Cube, again, we all know what a cube is. So a cube is probably the most basic regular type of polyhedron that we know of. Again, in a cube, all the edges are equal, all the angles are equal, all the faces are the same type of square. So everything's the same. So if this was like 5, then everything here is 5. Every side is 5, essentially. Octahedron is basically what you get when you take, two square pyramids and kind of slap them together. So an octahedron, again, 8 faces, so octahedron. A dodecahedron, which again looks like this. Again, kind of like pentagons all connected to each other in this sort of honeycomb that's kind of curved in on itself, essentially. And then an icosahedron, which again, is basically an equilateral triangle, and you connect them all to each other to kind of make this sort of dreidel-looking thing almost. Not quite a dreidel, but these are actually very common types of die used in various tabletop games and whatnot as well. So if you think about a 20-sided die, that's usually kind of like an octahedron. An 8-sided die is usually an isosahedron is a 20-sided die. An 8-sided die would be more like an octahedron. And then obviously a cube is a 6-sided die, and so on and so forth. But these are the only types of regular polyhedron there are. And again, they're specially named called Platonic solids just because they're that important in higher level geometries. So you cannot have a 21-sided regular polyhedron. If you have 21 sides to your polyhedron, it cannot be a regular polyhedron because isosahedron is the biggest it goes to. So, what about the non-polyhedron too? We have to make sure we talk about their names too. So the non-polyhedrons come in three forms. Actually four, but we kind of ignore the torus in this course. So a cylinder is basically a circular prism. So a lot of these are basically the circular versions of what we just talked about. So a cylinder is a circular prism. A cone is a circular pyramid. So remember, a prism is when you took two polygons and connect their corners. Well, a cylinder is when you take two circles, but because they don't really have corners, it's kind of weird to say. But if you take two circles and connect their circumferences together, that's what you get when you get a cylinder. So it's basically like a circular version of a prism. And a cone, again, same thing for a pyramid. A cone is, instead of having a polygon on bottom, you have a circle on bottom, and you connect all the points on the circumference to a single point on top, and that gives you your cone, or again, your circular pyramid. A sphere doesn't really have an analogy like those two do, but you can kind of think of it as a 3D circle. So if you take a circle and kind of spin it around like a coin, like if you take a coin on a table and spin it around, the image that that makes when spinning really fast is what a sphere is essentially. So a sphere is basically me taking this circle and flipping it over and over and over and over and over and tracking that movement, and that gets me that spherical shape or that ball shape essentially. So it's kind of like the oddball out among the three there. It doesn't really have a 2D analogy, but if you think about it as kind of like a circle spun in on itself, that's how you get a sphere. And luckily for us, even though they're slightly different, they actually share many of the same formulas, just with circle versions of them. So instead of doing, base times height, you'd be doing pi r squared, because you're dealing with circles in these cases, not rectangles or triangles. So they are a little bit different, but they have much of the same kind of overlap at heart. Whoops. So again, those are kind of the naming conventions of this. This was the main goal of this lesson here, is just to get you used to the language that we're going to be using. So again, the key terms being, what makes a prism? How is it different than a pyramid, essentially? How are cones and cylinders different / the same as prisms and pyramids? That sort of thing. That way, when we use these terminologies to talk about problems and talk about formulas and whatnot, we kind of know what we're coming from. So hopefully this video gave a decent introduction to the next chapter. If you have any questions, let me know. Otherwise, have a good day.